Hi guys, today we're looking at proof by induction involving series. So this is exercise 4.1. We're going to look at question 12. So prove by induction that 10 plus 10 squared plus 10 to the power of 3 all the way to plus 10 to the power of n is equal to 10 over 9 times 10 to the power of n minus 1, where n is an element of a natural number. Okay, so when we're looking at a proof by induction, we follow the same steps every time. So step 1, we want to prove the proposition is true for n is equal to 1. So we need to show that this is true when n is equal to 1. So substituting in n for 1, we get 10 to the power of 1 is equal to 10 over 9 times 10 to the power of 1 minus 1. So our left hand side is equal to our right hand side here. 10 is equal to 10. Therefore, it is true for n equals 1. In step 2, we assume that the proposition is true for n equals k. So we assume that when we substitute in n for k, this is true also. That means that 10 plus 10 to the power of 1 plus 10 to the power of 2 plus everything up to 10 to the power of k, adding all of those together will give us the same value as 10 over 9 times 10 to the power of k minus 1. In step 3, we have to prove that the proposition is true when n is equal to k plus 1. So we have to now prove that this is true for any term added on after k. i.e., we want to prove that 10 plus 10 to the power of 1 plus 10 squared plus 10 to the power of k plus 10 to the power of k plus 1, the term after k, is equal to adding all of these values together. So if I add all of these values together, I will get the same thing as 10 over 9 times 10 to the power of k plus 1 minus 1. Okay, so that's what we're trying to prove. So how are we going to do that? We are going to simplify our left-hand side and simplify our right-hand side and show that we get the same thing on both sides. Let's start with our left-hand side. Well, we know from step 2 that 10 plus 10 to the power of 1 plus 10 squared plus 10 to the power of k is equal to 10 over 9 times 10 to the power of k minus 1. So that's assumed from part 2. So wherever I see 10 plus 10 to the power of 1 plus 10 squared plus 10 to the power of k, we can substitute in 10 over 9 times 10 to the power of k minus 1 because it is assumed that that is true. This gives us 10 over 9 times 10 to the power of k minus 1, and then plus, so plus the term after this, 10 to the power of k plus 1. Let's simplify this. So I'm going to expand out my brackets. So 10 over 9 times 10 to the power of k gives me 10 times 10 to the power of k over 9. 10 over 9 times minus 1 gives me minus 10 over 9. And then we can separate out our exponent using our exponent rules, which are found on page 20 of your log tables. We know that a to the power of n plus m is the same as a to the power of n times a to the power of m. So when you have two exponents added together, it is the same as multiplying these two values with the same base, which means that 10 to the power of k plus 1 is the same as 10 to the power of k times 10 to the power of 1, which is 10 to the power of k times 10. Okay, so from here we're going to continue to simplify. So I am going to find my common denominator of 9 and add these terms together. So this gives us 10 times 10 to the power of k over 9 minus 10 over 9. And for our third term, our common denominator is now 9. So 9 times 10 gives us 90, which leaves us with our fraction of 90 times 10 to the power of k all over 9. We can now add together like terms. 10 times 10 to the power of k over 9 plus 90 times 10 to the power of k over 9 gives me 100 times 10 to the power of k over 9 minus 10 over 9. Okay, let's look at our right-hand side. Our right-hand side is equal to 10 over 9 times 10 to the power of k plus 1 minus 1. Let's expand our brackets. Remember, we're trying to show that our left-hand side is equal to our right-hand side. So we want to expand our brackets to this. So 10 over 9 times 10 to the power of k plus 1 minus 1 gives us 10 over 9 times 10 to the power of k times 10 minus 1. So again, we're just using our same exponent rule to separate out our exponents here. Multiplying this out, and we get 10 over 9 times 10 to the power of k times 10 gives us 100 10 to the power of k over 9. 10 over 9 minus 1 gives us minus 10 over 9. So we can see here that our left-hand side is equal to our right-hand side. Therefore, our proposition is true for n equals 1. And if the proposition is true for n is equal to k, then it'll also be true for n is equal to k plus 1. Therefore, by induction, it is true for all n values which are elements of our natural number.